everybody. Thank you to the organizers for the conference, for this NASH conference. I will talk about an historical point, which is the history of the Kelvin-Helmholtz instability, which is perhaps the most famous instability in fluid mechanics, apart from the Tolbian-Schlichting instability, which drives the transition to turbulence. So there are very famous pictures of this instability, in particular, which is a picture taken in United States, in the Colorado, which shows waves, typical Kelvin-Helmholtz waves in the atmosphere at the interface between the lower layer, which is a cold and heavy layer, and an upper layer, which is lighter, and so the contrast of humidity creates this. Creates. We see these waves. Another illustration is here. It is the mixing layer between two fluids moving upwards. Here, pure water on the left and bubbles on the right. And the third illustration is here is the instability which appears on the interface between a jet and then the quiescent ambient fluid. Of course, many illustrations of pictures of this instability. So the seminal paper is that of Kelvin-Helmholtz in 1868, whose title was On Discontinuous Movements of Fluids. In this paper, Helmholtz pointed the importance, the conceptual importance of discontinuities between fluid layers in inviscid fluids. And he said that the Euler equations do not allow for the existence of flows with surface of discontinuities. And these surfaces, discontinuities of the velocity. And these surfaces might be important in the analysis of problems. And Helmholtz said the remarkable sensitiveness to sound of a cylindrical current of air impregnated with smoke has already been described by Dr. Tyndall. I have verified Dr. Tyndall's experiments. This is clearly a property of the surfaces of separation, which is of the greatest importance in sounding musical pipes. So one of the main interests of Helmholtz was in musical instruments. Remember that Helmholtz has a chair at the beginning of physiology, and he was very interested in the physiology of the ear in relation with music. So this points out that whatever an irregularity is formed on the surface of an otherwise stationary current, this must give rise to a progressive spiral unrolling of the corresponding part of the interface. The corresponding portion, moreover, advances along the current. So there is here a clear description of the wave, but Helmholtz does not provide any calculation of the waves. This is, we can say, a qualitative paper on these waves. And here you have a picture of the situation Helmholtz had in mind. It is the formation of a wave at the exit of a jet, which hint the reed of a musical instrument, which can be an organic pipe or any other air. Paper is a very different, quite different paper by William Thomson, which was a friend of Helmholtz. They were sailing together, and it's a paper published in the Philosophical Magazine. But in fact, it's a letter. It's a letter of William Thomson to Peter Tate, and the Philosophical Magazine was publishing letters from one people to another. And in the part 3 of this paper, Helmholtz, which is entitled The Influence of Wind on Waves in Water Supposed Frictionless. So this is a letter at this day. And in this part, Thomson, the future Lord Kelvin, calculates the wave velocity at the interface of water and air governed by inertia and with the stabilizing effect of gravity and surface tension. So, here there is a clear calculation, a linear stability or linear analysis, which is very close to what we do today. And in particular, Kelvin shows that with no wind, waves with wave number k travel with this velocity, where here you have the gravity, here the surface tension gamma, and r is the ratio of the densities, which is very small for air and water. And when we introduce velocity v for the wind, the wave velocity becomes this, and hence instability, that is a complex wave velocity c, for wind velocity greater than this, this value, which is the minimum velocity appearing of the waves with no wind, divided by the square root of the density ratio. And here is a picture of this situation. Here is plotted the square of the wave velocity without wind, and instability appears when the square of the wind velocity reaches the minimum of this curve. And so that was the part 3, and 2 months later, no, not 2 months, 1 week later, Kelvin sends another letter to Peter Tate, and where he clearly indicates the existence of this minimum velocity, which is 23 centimeters per second, with a corresponding wavelength here. And Kelvin says the least velocity of frictionless air that can raise a ripple is 660 centimeters per second, which is 12.8 nautical miles per hour. Observation shows the sea to be ruffled by wind of a much smaller velocity than this. Such ruffling, therefore, is due to the viscosity of air. So this is the first, Kelvin posed a great problem here, is that the Kelvin-Helmholtz mechanism cannot account for the actual velocity above which we observe waves. The predicted velocity is much higher than that which is observed. And two months later, in part 3 of the paper, another letter where Kelvin says the influence of viscosity gives rise to a greater pressure on the anterior than on the posterior side of a solid moving uniformly, uniformly relatively to a fluid. Hence, if a regular series of waves at sea consisted of a solid body moving with the actual velocity of the wave, the wind would do work upon it. So this is Kelvin understands that we have to take into account viscosity in order to understand to understand better the problem. And here, I don't read the details, but Kelvin explains that he understood the importance of the minimum velocity with a remark by Freud to Scott Russell's a velocity of less than half a mile an hour does not perturb sensibly the smoothness of the reflective surface. If the air have a velocity of about a mile an hour, the surface of the water becomes less capable of distinct reflections, that is, small waves begin to appear, owing to the presence of those minute corrugation of the superficial film which form waves. So this is the first indication that turbulence may be the starting point of the pressure fluctuations induced by the turbulence of the air acting on the water may be the starting seed for the growing of large waves. So, and the third important man in the story is Rayleigh, who a few years later studies the inviscid parallel flow, the stability of inviscid parallel flow with continuous velocity profile u as a function of the vertical of the transverse direction. And from the momentum equations for small disturbance, Rayleigh first notes that a velocity jump across the interface implies that the growth rate diverges with wave number. The instability increases without limit with K. The application of this result to sensitive jets would lead us to the conclusions that their sensitiveness increases indefinitely with pitch. A probable explanation of the discrepancy readily suggests itself. The calculations are founded on the supposition that the changes of velocity are discontinuous, a supposition which cannot possibly agree with reality. And so this leads Rayleigh to another calculation where Rayleigh introduced a vorticity layer of thickness B. So the velocity varies continuously now from minus V below to plus V above with a vorticity layer. So this is a piecewise linear velocity profile. Fully to include the effects of friction would immensely increase the difficulties of the problem. For the present, at least, we must treat the fluid as frictionless and be satisfied if we can obtain solutions for law of stratifications which are free from discontinuity. And Rayleigh shows that in this case, we obtain this dispersion relations which relate the frequency of the waves to the wave number. And for long waves, that is small, the wave long compared to the thickness B of the vorticity layer, we recover the discontinuous case. But for short waves, then the n square is positive. That is, we have only waves propagating at the interface without any instability. That is capillary waves. So we see that the instability is greatest when Kb is equals 0.8 nearly. That is when the wavelength equals 8 times the thickness B. And the passage from instability to stability takes place when Kb equals 1.3 nearby, or when wavelength equals 5 times the thickness B. And in the same paper, Rayleigh provides a general result for parallel smooth parallel flow U, which is known now as the inflection point theorem, which Rayleigh explains like this, so that if the velocity curve is either fully convex or fully concave for the space between the limits at which the vertical velocity vanishes, the motion is thoroughly stable. So the presence of an inflection point in the velocity profile is a necessary condition for instability. An important step is the calculations introduced by Louis Rosenhead, so half a century later, which studies the nonlinear effect, the nonlinear contribution to the development of the wave. And so Rosenhead integrates numerically by hand. There were no computer at the time of the motion created by a discrete distribution of vorticity, and the vorticity is distributed along the interface, and the time development shows the famous unrolling of the wave, which is characteristic of this instability. And Rosenhead understands that the second harmonics distorts the sinusoidal wave front steeper than tail. And but Rosenhead also said no attempt is made to discover that value of the wavelength, which ultimately becomes dominant in the disturbance and so fixes the distance between successive vortices. And now we can ask the question: are these results applicable to real fluids which have some viscosity? And the answer is that viscosity thickens the vorticity layer on a certain time scale, which is the square of the thickness divided by the viscosity, so that inviscid analysis may be relevant, provided that the growth time is much smaller than the viscous time, which means that the Rayleigh number built on the thickness of the layer must be large, which is a reasonable conclusion. And viscosity has a second effect, in that it also reduces the growth rate and the cutoff point number, which has been studied by a certain number of people from from Betchoff and Chichnik in 1963 up to numerous people. And later, some additional effects have been introduced in the problem, such as continuous density stratification, rotation, magnetic field, etc., with a number of persons, including Taylor and Chandrasekhar. Now, what are the experimental proofs of this instability? The first experimental discussion is that of Reynolds in his famous paper where he studies the transition from laminar to laminar positive flow to turbulent. And Reynolds shows pictures, not photographs, but drawings of the instability. He studies this in a tube which is closed with two layers with different, so a glass tube 5 feet long and 1.2 inch in diameter, are filled with bisulfide of carbon, which is a little heavier than water, and then filled up with water. So two fluids, and the tube is closed at the extremities, and it is tilted. So the upper layer goes up, the lower layer goes down, so there is a shearing at the interface, and we see here the instability with waves. And Reynolds says at a certain definite inclination, waves nearly stationary showed themselves, presenting all the appearance of wind waves. These waves first made their appearance as very small waves of equal lengths, the lengths being comparable to the diameter of the tube. When by increasing the rise of the velocities of flow were increased, the waves kept the same length but became higher, and when the rise was sufficient, the waves could curl and break, the one fluid winding itself into the others in regular eddies. So this is exactly the description of the Kelvin-Helmholtz wave. But Reynolds made no reference to Kelvin nor to Helmholtz. And then Reynolds says, having found a method of integrating the equations for frictionless fluid, I obtained the results that flow in one direction was stable, flow in opposite direction unstable. So here you have an experimental demonstration of the Rayleigh theorem in some sense, but the calculations are not given by Reynolds, and there is no reference to Rayleigh. Then the most famous experiments are those performed much later by Thorpe, by S.I. Thorpe, which at the National Institute of Oceanography in England. And there was a series of 3 papers by Thorpe. In the second paper, Thorpe studies immiscible fluids and says that in the first paper, he described a technique first used by Osborne Reynolds to produce a stratified shear flow under controlled conditions. And Thorpe says, most of this paper, in fact, is theory. It's a generalization of the situation of the Kelvin-Helmholtz situation, where the fluids are accelerating, because here the velocity are not constant but increase with time. So Thorpe says quite good agreement is found between the times at which instability is first observed in the experiment and those predicted by a theory based on Kelvin-Helmholtz instability. And in the third paper, Thorpe studies miscible fluids, and it is in this paper that the photographs are absolutely wonderful. And so this photograph is found in many books and many papers. But curiously, Thorpe made no reference to the waves observed by Reynolds in either paper, and even the Reynolds paper is not cited in the references. But that was in 1970. But in fact, very nice photographs of this instability were shown in the years 1930. So that was in Toulouse at the Institute of Fluid Mechanics. The study was made by Charles Camichel, who was the head of the institute, and one of his students who was Etienne Cross. And the experiment is here. It's a large tube of 30 centimeters in diameter, which is, and the flow is created by a large tank, and which drives, and gravity drives the water to this tube, and the tube is closed is half closed by a plate, which occupies the lower part of the tube, and so that this plate creates a shear layer downstream at the level of the end of the plate here. And so this is a sketch of the flow. So here is the plate. The flow is from up to down, is downwards, and a wake is created in the wake, in the downstream of the plate. And here is the visualization of what happens. These four photographs are the four photographs in time, so the development of the wake with time. So here we see nothing, but here we begin to see some undulations of the separation surfaces, of the discontinuity surfaces. Here we clearly see some waves, and here we have the waves with the characteristic unrolling. And I just mentioned that here the scale is 1 centimeter. So these waves have a typical wavelength of the order of 1 millimeter. It's very small wavelengths. And Camichel and Cross measured the period of these waves as a function of the velocity for 3 fluids with different viscosity, and they plot the results here. So at the time, the way of plotting dimensionless things was to simply here plot the velocity divided by K, which is the ratio of the viscosities of the fluid, and a reference viscosity, which is here that of water. And in here we have the period of the wave multiplied by K, so that all the points for the different viscosities are on the same curve, fall on the same curve. And if you look here that when you double the velocity, the period is divided by 4, which means that this curve must correspond to something like V square multiplied by T divided by the viscosity equals approximately 200. And so this was published in the thesis of Etienne Cross, and also in the notes to the Academy, to the French Academy of Paris. And in these papers, and there is reference to Helmholtz and to the Reynolds similitude, but no interpretation, no physical interpretation. So if we try now to do the interpretation of these results, we can say that for the wave period equal to lambda over c, and taking for lambda the most amplified wavelength from the calculation of Rayleigh, which is 8 times the thickness of the boundary layer, of the vorticity layer, divided by the wave velocity, which is half of the velocity of the fluid velocity, and taking for delta. Oh, this is 5 minutes. Okay, and if we consider the growing thickness of the vorticity layer, we find that this at the distance, we find that the product, which is here, which is a kind of Reynolds number, is 100, about 100, the ratio of an advection distance divided by lambda. So the parallel flow corresponding to these observations corresponds to a distance from the plate of 1.6 lambda, which is a reasonable result. This means that the waves we observe corresponds to that which would grow on a flow invariant in the x direction, with a thickness which corresponds to that at the distance 1.6 lambda. Camichel and Cross also show interesting things, like here the vortex pairing, So here they follow two. So these are the photographs at different times, and if we follow these two crests, we see that they will merge. And here another illustration of the same phenomena. And Michel and Cross also observed that the Kelvin-Helmholtz instability may grow on the large starting vortices. You see here the starting vortices in the wake, and we see here Kelvin-Helmholtz waves growing on this unsteady vortex. Now, if we go back to wind waves, there were many tentatives to understand the discrepancy with the Kelvin-Helmholtz situation. So I don't enter the details. The problem was to understand how viscosity may act in order to create another pressure component out of phase with the pressure with the elevation of the interface. And there is a good paper in 1954 by Herschel, whose title is Wave Generation by Wind. But he collects many results, experimental results, which show a large discrepancy. And in fact, these experiments show the importance of the fetch in the problem. And a new mechanism an important mechanism was found in 1957 by Miles. But I think I have no time to explain this new mechanism, which is an important mechanism, which is an inviscid mechanism, which is based on the fact that there exists above the wave a critical layer where the fluid velocity is equal, the air velocity is equal to the wave velocity. And this introduces a singularity in the Rayleigh equations, and Miles is the first to have analyzed these situations, and where by which he showed that a pressure as a component in phase with the wave slope, which is proportional to the curvature of the. So negative curvature, which is a current situation in the air, negative curvature implies instability, and energy is then transferred from wind to the traveling wave. And accounting for viscous dissipation in water and assuming logarithmic profile allows the calculation of some critical velocity, which is about 100 centimeters per second, which is much close to the observations. However, the mechanism of this instability is not clear in the paper by Miles, and this was clarified by a very nice paper a few 5 years after that by James Lighty. But I think I have no time to explain the mechanism. So thank you very much.
Long live India and France friendship.